So let's get started with this. These are your notes. Today's like the 6th of October. What do we know about electrons? Are they positive or are they negative?
Negative.
Electrons are negative. Are they in the nucleus or out of the nucleus? Okay. Specifically, where are they if we're thinking about outside the nucleus? You said on the electron cloud, okay. So in the electron cloud. Okay, cool with that. Now, if we continue on this thought, outside the nucleus in the electron cloud, okay. So if I was to draw an atom with the nucleus in the middle is the N, that's why I write in there, nucleus. Remember, what's the charge of the nucleus, basically?
Positive.
Very good. Why is it positive? Yeah, the protons and the neutrons don't count. And what you're seeing here are the different energy levels, right? How many energy levels have I drawn? 3. Where's energy the lowest? Okay, so I would say this is the lowest energy. And I would say that this is the highest energy. Cool. I'm going to give you 2 instances real quick. 2 different things that could happen. Let's show this one first. There's an electron right there. And let's say that the electron is shifted to this outer level, to a higher energy level. So if you look at this movement, I think we could all agree, quite simply, that the electron that's here has gone from high to low or low to high energy. So the electron has gone from low energy to high energy. Good. Now the term low energy versus high energy I think is a little simple, so I want to elevate the vocabulary a little bit. So instead of saying low energy, I'm going to actually throw in a new term, and instead of saying high energy, I'm going to throw in a new term. So instead of low energy, I want to say that this is maybe like the normal level. We're going to call it the ground state. So this electron has gone from the ground state, the lower energy level, to a higher energy level, and let's call that the excited state. When you're excited, do you have lots or little energy? Lots. You know, if someone says, you know, you're getting, I don't know, I'm getting a new t-shirt from Walmart today. There's a good one. I get all excited, right? So I have tons of energy. Now then what if they say, I'm just kidding? Thank you. Aw. I'm very sad, because as you can tell, I don't have a lot of these shirts. I seemingly wear them repeatedly over and over. So I think then you would do the reversal and go back down, right? So what would we say in this case? The electron has gone from what to what? Okay. The electron has gone from a high energy state to low energy. And just like before, instead of saying necessarily high energy or low energy, we could say, I think Eric had said it just a while ago, you go from the excited state back down to the ground state. Marty? Hi. Thank you. In which case were you losing energy? In the first case or the second case? Do what?
Second.
The second. Okay, so I think we would want to write down that in this case you are losing energy. And in the case of the above one, this would be actually a gain of energy. So really kind of want to make sure we see those two hand in hand. Cool? We all good?
Yeah.
All good. Very good. Okay. I want to shift gears a little bit, and I want to talk a little bit about waves. This movement is a wave-like movement, so I want to talk a little bit about waves. So I'm really switching gears here. So I'll ask one last time, are we all cool with what I just did? This idea of ground versus excited state of electrons. Let's talk about waves. What is a wave, somebody? Very good. That's a wave. Periodic, right? That means that it's, much like the periodic table, it's a pattern. It's a repetitive operation. We draw out a wave. I'll draw out one for you real quick. We could identify a couple of important parts of a wave. Okay. No, we're really not too concerned with it actually right now. Now I want to ask you a question real quick. Is the wavelength big or small on the left or the right hand side? Yeah, wavelength is huge over here, right? What can you tell me about the frequency at this time? Is it a very low or high value? Low. And then over here the frequency was high, but what was the wavelength? Okay, so right away I think we should realize that you have this kind of inverse relationship, right? There is an indirect or inverse relationship. That's between the wavelength and the frequency. What does that mean? Is one goes up, the other goes down. So when wavelength is high, the frequency is low. Which means they have to be related by an equation. And let me give you the equation. Formula. Important formula. C is equal to lambda times frequency. So what does the upside down y represent again? Wavelength. What does the V represent? Very good. And what about C? Does anyone know that one? We haven't talked about it yet, though. Speed of light. Speed of light. So basically, the speed of light is equal to the wavelength times the frequency, and the speed of light is a constant Its value is 3.00 times 10 to the 8th meters per second. You know what a meter is, and you know what a second is. That you go that many meters in 1 second, 3.00 times 10 to the power of 8, that's basically very fast. Well, light is very fast. Something that we're going to work on in class together over the next couple of days, today and tomorrow. So you don't even really need to write on this, so just pass this out now rather than later. We have our badges today. Badges. Excuse me. The unit of wavelength should be in meters, because you measure distance or length in meters. The frequency should be in either hertz or 1 over second or second to the minus 1. Those are the possible units of frequency. Now, what does this mean? Well, if you know the speed of light and the wavelength, you could find the frequency. Or if you knew the speed of light, which you do, and you know the frequency, you could find the wavelength. Once you know 2 variables out of 3, you can find the third. So let's look at this. Let's look at that first problem on the paper I just gave you. Of course, you might need out your calculators. But in problem 1, it says calculate the W, or I'm sorry, not W, the upside down Y. What does the upside down Y represent? Very good. Given it the V, what does that mean, the V of radiation? The frequency, right? Right? Okay. So what formula are we going to use? Not all at once. Jennifer, what formula are we going to use? Okay. Very good. And which of these two do we know? Do we know C? Yes? Yes. It's a constant, right? Do we know the wavelength? No, because that's what we're supposed to find. Do we know the frequency? Yes, so let's put everything in there. 3.00 times 10 to the 8th meters per second is equal to the wavelength, which we do not know, times the frequency that we do know, 5.10 times 10 to the 14th second minus 1. Keep your parentheses here. How are we going to solve for that lambda? Divide both sides by what? Brianna? What are we going to divide both sides by? We got to get this variable by itself, right? So we're going to divide it by this guy.